Hello and welcome to our little online Analyst contest run by the Department of Chemistry at Swansea University. This is just intended to be a bit of fun where you see some experimental data and then do some calculations that are based on the calculations that I'm fairly sure you all will have done by now. So anyway, we're going to study this reaction here. It's a redox reaction for those of you who have done reduction and oxidation, although we're not going to be very focused on that here. We're just going to be focused on the stoichiometry of the reaction. So anyway, you take C2O4 2-, that's an anion called oxalate, and you can get it into aqueous solution by dissolving up some sodium oxalate, some potassium oxalate, or as we're going to do in this particular experiment, dissolve up some ammonium oxalate to get this into solution. You then react it up with some potassium permanganate, which is a nice beautiful purple color, one of my favorite compounds in the whole world, potassium permanganate, in acidic conditions. The H+ there means that you have acidic conditions for it. Now, you'll encounter permanganate, MnO4- as an anion, quite a lot as you go through your chemistry career because it is a super duper oxidizing agent. And it's an even more fun oxidizing agent because its behavior is different whether you're in acidic solution or neutral solution or basic solution. Anyway, we're in acidic solution here, so remember that in a few seconds. Anyway, so what happens is that the potassium permanganate is reduced, and as it is reduced, it oxidizes the carbons in this oxalate. So one of the products that we make is carbon dioxide and water, and then the manganese goes from the manganese in the 7+7 oxidation state in permanganate down to 2+ oxidation state in the product. And this Mn2+ we essentially think of as being colorless. It's actually, if you take a really concentrated solution of it and you look at it using a spectrometer, then you can see that it's actually got a teeny little pinkish color to it, but I don't want you to think about that right now. I want you to think of it as being colorless. So this is the reaction we're studying. We're going to take a colorless solution, ultimately, of this oxalate. We're going to add to it a purple solution with this permanganate with acidic conditions, and we're going to do this redox reaction where essentially the purple solution ends up being colorless. And we're going to do this reaction twice in two different ways. The first thing in part one is we're going to take a known amount of our ammonium oxalate, and we're going to use that to determine the concentration of a solution of potassium permanganate that I made up. So we're going to do the reaction knowing this and determining how much of the permanganate we need to add to completely react with all the oxalate. And of course, the way that we'll know that all the permanganate that we've added has completely reacted is we get a colorless solution. Then in part two, we're going to take the permanganate solution, which we know the concentration, and then an unknown solution of ammonium oxalate, and you're going to use the known permanganate solution to determine the concentration of this unknown oxalate solution. Okay, so keep that in mind as we're going through two parts of it. Two solutions, permanganate solution that I've made up that I know the concentration, but you don't. An oxalate solution that I've made up that I know the concentration and you don't. First thing, we're going to determine the concentration of the permanganate solution by using a known amount of oxalate. And then once we've got the concentration of that permanganate solution, then you're going to determine the concentration of the oxalate solution. And we're going to do all of this using titrations.